Okay, so that's a brief primer of the global carbon cycle. Let's conclude with the podcast on summary. This is now the canonical figure that always shows up whenever you say global warming or carbon cycle. This is one of the first figures that pops to mind and is used widely, and fortunately continues to be maintained with additional locations at other places in both hemispheres. If we take away the seasonal cycle, then we will get a trend of the fossil fuel carbon increase, and if we take a derivative of that, then we'll get interannual variabilities, as we will see later on. So I took some figures from Pierre Friedlingstein's paper and this book by Jorge Sarmiento and Nikki Gruber, a really detailed, nice book. There's another book by Williams and Follows, Mick Follows from MIT, and Williams from the UK. Anyway, starting with this figure from the Sarmiento book, which is also from the Archer paper, it is showing fraction of anthropogenic CO2 and the fossil fuel release of petagram carbon on various ranges, and where it would end up over time. So on the very long time scale of the CO2 weathering time scale of 100,000 years and longer, where we said carbon cycle has a negative feedback, we have silicate weathering, drawing down the CO2 that's put into the atmosphere, which eventually makes it into the ocean through the rivers by weathering, dissolving of CO2 in the rainwater, weathering into the ocean, metamorphic rocks, and then back, right? There is terrestrial calcium carbonate cycle, which takes about 10,000 years. So seafloor calcium carbonate cycle takes about 4 kilo a year. You know that this has got that carbonate pH stat that we talked about. So if you dissolve more carbon into the ocean, the pH decreases, then calcium carbonate dissolves, and unless you balance it with runoff from the terrestrial calcium carbonate, you're going to keep dissolving calcium carbonate to make up for the pH. So there is a balance, there is a pH stat involved there. And then there is the ocean invasion, which is a much faster time scale of 300 years. So if you look at something like an emission of 400 petagrams, then you can expect that you take out about 87% by these two processes here in terms of seafloor calcium carbonate and ocean invasion, for example. That leaves about 13% in the atmosphere. So what are we worried about in the future? It's just about how much do we really know. We talked about long-term CO2 weathering thermostat that's stabilizing, and the Ice Age carbon cycle that was a positive feedback, unstable. And we said in the 20th century, since Industrial Revolution, basically the CO2 that's being put out by humans is being taken up by various things like the ocean, land, and some accumulates in the atmosphere. So it's damping, so it's stable. But where are we headed in the future? So we'll just look at some of the problems we are facing, and essentially carbon cycle remains a big unknown as of now. So here we are, the figure that we looked at, where we estimate air-sea CO2 flux, which is out of the ocean into the atmosphere here, because you have very strong upwelling, and despite the biological fixing of carbon by photosynthesis, upwelling drives nutrients, photosynthesis, enough light at the surface, etc. But the solubility pump of upwelling and increasing the seawater PCO2 dominates, so the carbon dioxide is coming out of the ocean. This contributes probably about 70% to the interannual variability of CO2 across the world in the atmosphere. So it's one of the largest signal to noise ratios in terms of the measurements we have. And you can see here the magnitude of interannual variability, which is obviously related to El Nino. If you don't know what El Nino is, you can go and watch some podcasts and on my channel. But this is where the changes in upwelling and temperature happen on El Nino and La Nina timescale. So you think models would have this nailed down by now, but actually if we do what we said with the Keeling curve of removing the seasonal cycle and looking at the trends, here are the fossil fuel emissions since he started measuring them in the 1950s, keep increasing with various rates that have changed over time because of the fuel crisis and other financial crisis and other things. But when you take time derivative, year-to-year variability is clearly extracted, so you have ENSO events clearly affecting the interannual variability, as I mentioned. And what is taken up by the ocean and terrestrial biosphere and what is accumulating in the atmosphere is clearly seen in this case, right? But if you look at the model simulations of, I will come back to that a little bit later, of the El Nino cycle, we will see that they are not very close to each other. Okay, that's worrying. But what else do we have to worry about other than the things we already mentioned? Well, essentially these are what we are removing and burning and putting more and more CO2 into the atmosphere. Permafrost, we said, is frozen land in the northern latitudes which are warming faster because of the Arctic amplification. The thawing of the permafrost exposes 1700 gigatons of carbon to volatility. If it gets released, we are going to be in serious trouble. Look at the numbers here and look at the reservoir here. Soil carbons, of course, subject to perturbations due to agricultural practices, urbanization, deforestation, or just land degradation, warming itself driving respirations at a faster rate, and extreme events like extreme rainfalls and loss of hurricanes, storm surges, inundations due to sea level rise, etc. make this also vulnerable. Vegetation, of course, we are hearing about global warming increasing the intensity of the forest fires, which we have seen just now in Cape Town, South Africa, Australia, US, Canada, everywhere. Wildfires are a problem. Human management or human attempts to manage wildfires is also potentially adding to this problem, so we don't know exactly how that works. People try to figure that out. So whether land will continue to take up carbon or not, it continues to be an issue. Then there are, of course, perturbations of the surface sediments and deep ocean, warming penetrating deeper and deeper, ocean acidification and calcium carbonate cycle, wetlands getting drained or being lost because of other forces like extreme events and droughts and warming and so on. So all those remain big concerns. We said hydrates may not be perturbed worldwide, but even if they're perturbed in shallow regions like Siberia, that could be an issue. Looking for feedbacks, this is again another uncertainty. This is from the paper by Pierre Friedlingstein. If you want to look for a feedback factor, you would use a model where you have coupled carbon cycle and uncoupled carbon cycle, which means you have climate model with the carbon model, where the carbon model is not exchanging information in terms of the greenhouse effect with the CO2 changes, let's say. So there is no feedback from carbon cycle to climate. In that case, you can take the difference and divide by the total coupled system where there is an active feedback between the carbon cycle and climate. That gives you what is the feedback you would expect from carbon cycle climate feedback, and then you can split it into land carbon change because of carbon cycle perturbations and because of global warming, and both have a coefficient here. We're assuming linearity, which is not necessarily true. true, but these coefficients also have to be constrained properly using observations, as we will see in a minute. A similar equation can be written for the ocean, where ocean carbon cycle and ocean warming have contributions to the oceanic carbon storage change overall to the increase in anthropogenic carbon. To constrain it, we try to use observations. So here are the multi-scale carbon cycle interactions that we looked at. On longer ice age timescales, we said it's a positive feedback. So cooling is amplified by CO2, warming is amplified by CO2. And here you have the last millennium changes, including little ice age seen here. So you look at temperature anomalies and CO2 anomalies, and you also look at a shorter time scale of the, let's say, the Keeling curve with the warming and the CO2 changes, and you try to derive these coefficients of the feedbacks. That's the best you can do in terms of constraining the models. Having done all that, looking at here at global carbon budget over the historical period, adapted from the IPCC report from 2014, fossil fuel, so you can look at fossil fuel emissions with some uncertainty. This is land use changes here, wildfires, ocean uptake, and this is essentially talking about the temperature feedback. This is the carbon cycle feedback in these equations. So we're looking at beta 1, gamma 1, beta 0, gamma 0. And without going into too much detail, we are trying to use this data and this data to try to derive the feedback factors. But the main point I would take out of this is that look at the uncertainties here. The carbon cycle contribution to ocean, land uptake of carbon, and carbon cycle contribution to ocean uptake of carbon. The uncertainty here is almost 50%. Okay, 185 plus minus 90. Here it's 160 plus minus 30. As we said, land has got a lot of inhomogeneities and very regional features and so on. But even the feedback factor from temperature, emissions due to temperature feedbacks, warming, is highly uncertain, and the same for the ocean, almost 100% uncertainty here. Okay, so you can put that together for sources, sinks, and land uptake, again for 1750 to 2011. So emissions and land use change, well constrained here, not so well constrained here. Atmospheric increase is well constrained because we can easily measure it, but oceanic uptake has a significant uncertainty. Out of that, you have CO2 driven uptake and climate driven uptake. So temperature changes, dissolution changes, wind changes, air CO2 exchanges, and so on. And land uptake, not very well constrained at all. CO2 driven, also similar uncertainties, and climate driven, similar uncertainties. Okay, so that's the main point, that carbon cycle remains somewhat of a wild card going into the future. And the news for models again is concerning in the sense the region where we have the largest signal to noise ratio and good data, the models are not doing so well. So if you look at air CO2 flux of in the eastern why did it do that to me? In the Eastern Pacific, sorry about that, we can see that from 1980 to 2000 or so, there are measurements and there are atmospheric inversion calculations with these uncertainties in gray bands. And then there are different models, the MIT model, the French model called OPA, and there is the SOI index, which is tracking the El Nino. And you can see that the differences between models are substantial, right? And this is in a region where the signal is very large. Or imagine in the regions where the signal is small. So This is where we will leave it, in the sense that we know that carbon cycle is a big part of global warming, and carbon cycle is the main perturbation that is driving global warming right now, and yet we don't have a very good handle on it, so one has to keep that in mind. On top of that, we are trying to figure out how much carbon we can emit or how much we have to take down to stay within the temperature targets we are aiming for in terms of 2 degrees C or 1.5 degrees C by 2100, with a certain probability like 66%. Okay? Keep all these things in mind and keep looking out for improvements in understanding, modeling, and measurements.